Consider a one shell pass, two tube pass, shell and tube heat exchanger. Water is heated from 20 degrees C to 75 degrees C. For the water, the specific heat is 4.18 kilojoules per kilogram K. A process fluid enters the heat exchanger at 200 degrees C and exits at 130 degrees C with a flow rate of 5 kilograms per second. For the process fluid, the specific heat at constant pressure is 2050 joules per kilogram K. The overall heat transfer rate is 450 watts meters squared Kelvin. Find the heat transfer rate, the water flow rate, and the required heat transfer area. As we're doing this problem, we should keep certain things in mind. One is that the heat transfer from the hot fluid is equal to the heat transfer into the cold fluid, except with the negative side. In other words, whatever the hot fluid loses, which is going to be a negative value, is going to be equal to whatever the cold fluid receives as far as heat transfer. And we can calculate the heat transfer for each fluid individually by using Q dot equals M dot Cp delta T. And then for the heat exchanger, we can calculate the heat transfer by using Q dot UAF log mean temperature difference. Now, U is the overall heat transfer coefficient. Again, that includes convection, conduction, fouling, etc. And A is the surface area of the heat exchanger tubes. F is the heat exchanger coefficient. And delta TLM is the long mean temperature difference. So as we're going through this problem, we're going to have to keep these things in mind because eventually we want to find the area of the tubes. So we're going to need this at the end. So we have a picture something like this. We have our uh, water coming in this way, and it's coming in at 20 degrees C. And you could also, maybe this is going overboard with the notation, but you could also say over here the water is a cold fluid at 20 degrees C entering the TCI. And we know that uh, for this one, we don't know the mass flow rate of the water. And we do know that Cp of the cold is approximately 4.18 kilojoules per kilogram K. And we know for the hot fluid, the inlet temperature is 200 degrees C. And the specific heat for the hot fluid is 2050 joules kilogram K. I'll convert it to kilojoules since that's what we have above. Like this. And we do know the mass flow rate of the hot fluid. It is 5 kilograms per second. And let's see. And we know the outlet temperature of the hot fluid. 130 degrees C. And the overall transfer like this. We may eventually be wanting to convert this later. I think we're going to end up needing this to be kilojoules. So we could write this as 450. Remember, watt is a joule per second. So we can write this way. Or in terms of kilojoules, we'll have this. So now let's go ahead and calculate the heat transfer rate. Now we have enough information about the hot fluid to be able to calculate that. Again, remember, as I said a minute ago, whatever the hot fluid loses, the cold fluid gains, and vice versa. And so let's calculate the heat transfer of the hot. And again, we're going to use mass flow rate of the hot times the specific heat times the change in temperature of the hot fluid. And in this case, hot fluid was 5 kilograms per second. And CP of the hot fluid was 2.05 kilojoules kilogram K. And of course, remember, temperature differences, they're going to be the same for Celsius or for Kelvin. So we don't have to convert the temperature since we're taking the difference. And that's going to be 130 degrees C was the outlet temperature of the hot fluid, and 200 degrees C was the inlet temperature. Like this. So the heat transfer rate is 717.5 kilojoules per second. Again, it's negative because the hot fluid is losing that amount of heat. And now the cold fluid have the same amount of heat transfer except with a sign change. Next, we need to find the mass flow rate of the cold fluid. And again, we use this equation for heat transfer. Remember that QC will be the same as QH, just except with the change of sign. And so we can, from this, solve for the mass flow rate like this. And if we look back at our problem, well, first of all, it's 717.5 kilojoules per second. Again, whatever heat the hot fluid lost, the cold fluid will gain. And we know the CP value for the cold fluid is 4.18 kilojoules kilogram K. And we need delta T for the cold fluid, and that was 75 degrees C minus 20 degrees C, like this. When I put that in my calculator, I got a mass flow rate of 3.121 kilograms per second. As I mentioned before, remember that the we have a temperature difference here, so that even though this is degrees Kelvin here, the temperature difference will be the same whether we're doing Kelvin or Celsius. And so this is going to be kilograms per second like this. That's our mass flow rate. And we also have to find uh, the required heat transfer area. So we found the heat transfer, the mass flow rate of the cold fluid, the water, and we're going to have to next find the area required. Now, when we do that, we're going to need the log mean temperature difference. And so we have to look back at our picture. And so back up here, we look at, say, in this case, where the cold fluid came in and the hot fluid went out, because this is going to be counterflow. So we look up in this area here and look at this temperature difference. So here we have 130 and 20. And so again, you can call this T1 difference T1 or T2. It doesn't really matter. I'll call it delta T1. Again, you can either call this side T1 or this side T1. And so it's going to be 130 degrees C minus 20 degrees C equals 110 degrees C, like this. And then do the same thing down here. We have 20 degrees C, excuse me, 200 degrees C here. And at the shell outlet, I didn't write it down, but that was 75 degrees C. And so we'll call that delta T2. Again, you always take the highest minus the lowest. Like this. Again, just to emphasize, we called this side delta T1. We could have easily called it delta T2. And we called this side delta T2. Again, we could easily call it delta T1, but just choose one or the other. And then do your log mean temperature difference. And again, I'll put it this way. And once again, it doesn't matter which side you picked, is delta T1 or delta T2. And also here, it doesn't matter which order you put them at the top. The only extremely important thing is whatever you put over here goes in the numerator of the log, and whatever you put the minus with goes in the denominator of the log, like this. And so in our case, 110 degrees C, that's 125 degrees C, divided by the log of 110 degrees C, 125 degrees C. Again, that's the natural log. And we put it in the calculator, we get 117.34 degrees C is going to be our log mean temperature difference. Next, we'll find the area of the tubes, and keep in mind this equation here, the heat transfer rate Q dot is equal to the overall heat transfer coefficient. We know those two. We're going to solve for the area. We know the log mean temperature difference, but now we have to kind of find this heat exchanger coefficient. And for that, we're going to have to use a table in the book. And for that table, we're going to need R, and we're going to need P. And again, we're going to be using this figure right here. And again, we'll calculate R, which is a T for the shell, in minus T shell out. In the denominator, we're going to have T tube out minus T tube in. And P is going to be T tube out minus T tube in divided by T shell in minus T tube in like this. And so let's put some of those numbers uh, in here. So the T shell was this up here. The T shell in was 20. And then the T shell out was 75. And T tube out was 130. T tube in was 200. And then a T tube out was 75. Excuse me. T tube out was 130. And T tube in was 200. And T shell in was 20. And T tube in was 200. Like this. Now notice this one is kind of the one that's kind of out of order, so to speak. These were shell, shell, here, tube, tube, here, tube, tube, but here we had shell, tube. And when you put these values in a calculator for R, you get the 7857. For P, it's 3888. And when we look at the table here, again, in my book, this is table 13-7A. 13-7A. Let me see if I can focus this a little bit. So again, now we have for P, it's 3888, which is way over here. And then for R, it's going to be 7857. Actually, these all kind of converge back here. And so it looks like, and notice the 78, it will be coming right into here. It looks like we can say that in our case, F is going to be just about 1 because 3880 comes up here, and then 0.78 will be coming in here. So we can say from figure, again, in my book, this is figure 13-7B. F is going to be 1.0. This. So now we have just about everything we need. So we're going to use, for the heat exchanger, use this. And we want to solve for A, the area of the tube. Like this. We have calculated our heat transfer rate, which was 717.5 kilojoules per second. We had the overall heat transfer rate. Let me put in the kilojoules since that's what we have the heat transfer in. heat transfer coefficient is 0.45 kilojoules second m squared k, like this. And again, we determined F was 1, and the log mean temperature difference, which we just calculated over here, was 117.34. Again, that could be C or K. And put that in your calculator. And I got an answer of 13.59 square meters. So that's the area required, the surface area of the tube required to achieve what we want to achieve. And what we want to achieve is those temperature differences. We want to be able to put in water at 20 degrees C, X at 75 degrees C. The processed fluid, we want to go at 200 and X at 130. And we're going to need that much surface area in our heat exchanger tubes.